Hey guys, welcome to a new video. I recently did a video on LED strip power injection, and I've done one way in the past, like 1 or 2 years ago, and I've always linked those on my website, but I realized there's a lot of interest in those streams, but I never did a real video about it, so maybe a lot of people are missing them. So that's what this video will be. We'll sit down and we'll calculate power injection, or basically how to wire up your addressable LED strip. And we're going to learn everything today. So total amount of power you need, so you can size your power supply, the amount of injection points you're going to need, so that you can run your LED strip correctly and you're not dealing with voltage drop, the amount of power each injection point is going to use, and then what wire diameter you need to go to that injection point, combined with the amount of power we then know it's going to draw and the distance from your power supply or quinled board. I think that's going to be very interesting. We'll be looking at 3 different scenarios: 5 volt, 12 volt, and 24 volt, and I'll type those out in a notepad and you can follow along basically. I do advise you to watch all of them, because I'll be giving explanations as to why or how we're calculating certain things, and I might not do those as extensively in all the examples, but I will try and have jump links in the description. Alright, well, let's first go through some theory, and to do that we're going to go to a web browser. In this case, we're going to go to quinled.info, and there all the articles I'm going to talk about are in the digitally addressable LEDs section. So we can click on there. Here you can see all the controllers we can use. I'll also give some controller advice based on my own controllers. I have 4 digitally addressable LED controllers nowadays. The Dig-Octa, which is a small USB-C powered for 5 volt 3 amps. Then we have the Dig-Uno that can do 5 to 24 volt, up to 10 to 15 amps I'd advise. So Dig-Quad can do up to 30 amps and has onboard power distribution and fusing, and has 4 output channels. And then the Dig-Octa system can do 50 to 100 amps and has 8 channels and all kinds of upgrades. So I'll talk about that slightly during all the calculations and things like that. But what we're most interested in is some articles. For instance, here in the power related sections, we have the digitally the digital LED power usage sheet. And here we have a sheet for 5 volt, a sheet for 12 volt, and a sheet for 24 volt. And these are real world measurements. So for instance, if we look in the 5 volt sheet and we zoom in a bit, let's see here. First up, we have WS2812B, the generic strip we all use, and we can see that if we're running 100% red, we're drawing 25 watts. All these sheets are in watts, so that way you can compare 5 volt, 12 volt, or 24 volt, since watts are always the same. Also, these sheets are based off 60 LEDs a meter generally, or it will be noted, and 300 LEDs, so a 5 meter or 16-foot strip. But the main value we're going to use during calculations is going to be RGB white 50%. Why is that, you ask? Well, if you look at this sheet and you start comparing all kinds of values, you see in the more real world scenarios, if you look at police all 100%, or loading orange 100%, or rainbow 100%, we see 25 watts, 11 watts, and 25 watts again. If we look at the RGB white 50% value, we see that that's 33 watts. So that's slightly higher than any effect that I tested used. Also, single colors only use 25 watts. So again, the 50% white value is slightly higher than any single color. Now, dual color will come near the 50% white, so generally like 35, maybe 40 watts. But I think the RGB white 50% value is good to calculate with as a nominal value. Basically, I don't advise anyone to run RGB white at 100%, because RGB white looks horrible. It's basically a white colored light, but it's not white spectrum light. And I'll have an article linked down below about the CRI of light. But basically, addressable LEDs cannot be used as primary lighting. RGBW is slightly better. We also have some SK6812 here, which is RGBW. But still, it's CRI, so the quality of the white light is quite low. But yeah, we're going to be using the RGB white 50% value, and we can use the power limiter in WLED to make sure it never exceeds that. And that way we can adjust our fusing for that, so that if it did ever exceed that, our fuses would pop and will always be safe by a hardware protection. And software-wise, we can limit power so that it never exceeds, well, basically the scenarios we calculated for, so that it always will look good. I hope that makes sense. It is kind of a quick explanation. Basically, calculating everything for 100% white, you're over-speccing everything twice-fold for only one scenario you'll never use or shouldn't use anyway. And that's why we're going to use RGB white 50% as the values, because that means we use less power, thinner cables, etc., etc. Okay, hope that makes sense. A second thing we're going to state up front is that we know how much an injection point can use at maximum. The reason for that is there's a whole live stream you can see here, but I have another article, the how much can a single injection point handle article, and this basically goes into some tests I did where I tested with the default black JST plug we have on all our LED strips, or I snipped those off and wired the wires directly, or I used the JST plug plus the extra wires, or even I desoldered everything and I soldered on 16 gauge wire, which is quite thick, 1.3 millimeters square. And as you can see here, basically we could never get more than 4 amps and maybe a little bit into the strip effectively. The harder we would push it, the more voltage drop we would get. So for an edge injection, so if you have a strip, that means here on the side, at the start or at the end, we can only inject about 4 amps. Okay, that's a rule we're going to use. Second, if we have a middle injection, basically if you have a middle, you have copper going this way and copper going this way. That means we have twice as much copper near there. So we're going to state that a middle injection can handle a maximum of 8 amps. Okay, if you want to see those tests and you don't believe it and you're running your 60 amp power supply with a single injection and it's working fine, that's great, but physics still exists. And basically the copper layer on the strip is only, well, it's quite thin, so it's only so much. And that amount of copper can only carry so much current before, well, basically the voltage will start dropping and it becomes less or even useless to run more power. So that's why you have to run extra wires next to your LED strip, adding copper and then injecting that in a later point, because then you basically circumvent the resistance that copper builds up for more than 4 amps, and you're injecting it later in a path that doesn't have that resistance. So then, well, you have more power that can make it into the strip. And as I just mentioned, if you want to do that for RGB white 100%, and if you have a 5 meter 5 volt strip with 60 LEDs a meter, you will have to inject front, middle, and end to do that perfectly. Then you'll have a perfectly balanced strip in regards to voltage drop and power injection and things like that. But as I already mentioned, I kind of find that to be overkill. So what I would do is inject the front and the end. That will give us 8 amps that can make it into the strip, because the front injection can do 4 amps and the end injection can do 4 amps. An alternative method that you can use is injecting the middle of the strip, because that will also give us 8 amps. And, well, if we quickly check back in the 5 volt sheet, let me zoom in there a little bit. If we have 8 amps and it's 5 volt, and I'm going to go to my notepad scene here. I'm going to do all calculations using the calculator. If we have 5 volt times 8 amps, that means we have 40 watts available. Okay. Looking in our sheet, and these LED strips have all been tested by me in an ideal condition, so with many injection points, etc. So this is the most they can possibly use without suffering from any voltage drop. We see that RGB white is 33 watt, or a single color is 25 watt, or the effect that used the most uses 25 watt again. So if we have 8 amps we can effectively inject into our strip, either front end or middle, that's enough for running effects and single colors and things like that. Not for RGB white, but anything else than that it is. So I hope that kind of explains the rules we're going to use to calculate these things. Now let's define some scenarios, shall we? Scenario 1, and I'll probably be silent during most typing parts so I can speed those up in post. But yeah, so let me quickly specify a few scenarios, and then we'll walk through each of the steps how to calculate things. One moment. Okay, so we have 3 scenarios. We're going to do 20 meter each time. You'll learn, if you follow along, how to do it for 15, 35, whatever meters. 20 meter is 64 feet. I guess I should mention that. I can't guarantee I'll work with American lengths always. I do like using wire gauges, but I'll put a link on the description and in the video description where to find the voltage drop calculator we're going to use in this video. I'll also make this notepad available for download on my website, so I guess I should also put the link here. Okay, we're going to be using that voltage drop calculator. That reminds me of another rule. Basically, let me write down the rules. So, we're going to be using all power values from the power sheet. We're going to calculate with the nominal power value. That's always enough for effects and single colors, dual colors, etc. So that's RGB white 50%. We're going, edge injections can do about 4 amps, middle injections can do about 8 amps, and a power injection wire should never have or not have more than 10% voltage drop on that wire. And we're going to use this calculator, voltage drop calculator, to calculate that. So, scenarios, 20 meters each time, 5 volt, 12 volt, 24 volt, WS2812B, the strip and type of LED we all love and use, WS2815, which has some interesting caveats, and then WS2811, which is 720 LEDs per meter, but it's cob LED strip, so it's actually tuned at 40 LEDs a meter if you count RGB like on the other strips. But I have a whole dedicated video about that, and I really love this addressable neon strip, so you should really check that video out. Anyway, let's go to scenario 1. So we know that 5 meters, or 16 feet, uses. Let's quickly check that. It's over here, so we're back in our power sheet. WS2812B, 5 meters or 300 LEDs use, well, let's say 35 watts, right? Let's round it up a little bit. So 20 meters or 64 feet nominally needs or uses. So we go to our calculator, that is 35 times 4, 140 watts at 5 volts. Nope, I didn't. Sorry, I was on the wrong screen. Let's go through that quickly. Scenario 1, 5 meters uses 35 watt, that we got from our sheet, and then 20 meters uses 140 watts, that's basically 5 times 35 at 5 volt. Okay, so we know we have 20 meters, and we also know that we need to do 140 watt. but we only know how many amps an injection point can take. So let's see, 140 watt divided by 5 volt, that is 28 amps in total. So now we need to divide those amps over the injection points we need. But we don't know how many injection points we need, but we do know how we can structure it with the 4 and the 8 amp values. So let's see how our strips is constructed. We have a front, then we have a strip, and then we have a middle, then we have a strip, we have another middle, we have another strip, another middle, another strip, and an endpoint, right? And let me add a little thing here. So if we inject power at the front, let's do it here, and then, no, let's not do that. Let's not, okay, sorry. I'm figuring this out with you guys. If we inject power in the middle here, and then we inject power in the middle here, and then we inject power in the middle here, that means we have 3 middle injection points. That means we can do 3 times 8 amps. 3 times 8 amps is 24 amps, and we need 28 amps. Now, generally I'd say that's close enough. But we can say, okay, let's do a injection at the front too, and well, this kind of changes things, because now the first strip will be receiving power from the front, or let's say here, from the front, but also from the middle. So it'll start to take less from the middle point probably. But let's ignore that right now. Let's say front is 4 amps, middle is 8 amps, because that's our first middle. Second middle is also 8 amps, and the third middle is also 8 amps, right? Now this generally is probably, maybe it'll take a little bit less from the front. Would it? Yeah, no, it's 4 amps on both sides. That actually makes sense. No, this works. So this is 4 plus 8 plus 8 plus 8 is, Jesus. I was going to calculate everything, right? Calculate. Oops, 8 plus 8. No, I didn't do that right. 8 plus 8 plus 8 plus 4. 28 amps. So that matches the calculated value that we need nominally to satisfy the current requirements of the strip we have to run 20 meters of WS2812B. Okay, I hope that makes sense. We're doing a lot of middle injections. Once we raise voltage, so we go to 12 volt or 24 volt strip, we can do more with just front and back, or front, middle and back, or something like that. But as it is right now, with 4 strips, we can do 3 middle injections, and that kind of works out best. Okay. So now we know total amount of nominal power, how many injection points we need to satisfy that power demand, because, well, with our rules, we just have to make more power injections until we satisfy those rules, right? And now that we know how much power each point is going to use, we also kind of already know how far each point is going to be. Because if we take this over here, okay, let's say the front is 1 meter away. That means our first middle injection is 6 meters away, because it's a 5 meter strip. That means this one is 11 meters away, and this one is 16 meters away, right? So using all those values there, we can go to our voltage drop calculator and see what that comes out to. So let's go to our browser, voltage drop calculator, and we're going to leave it at 18 gauge for now. I like calculating cables in gauge, but there is a very, very simple AWG to millimeter square converter if you need one. So let's put it to meters, 1 meter. Let's set it to volts, 5 volts, and we want to be able to deliver 4 amps. Calculate. Okay, so let's say we use a thinner cable. I wouldn't go below 20 gauge. So let's say that 20 gauge is fine to do our front injection, right? So here we need 20 gauge. The first middle injection needs 8 amps and it's 6 meters away. Okay, let's go back to our browser. We need 8 amps and it's 6 meters away. Now we see we're dropping 3.1 volt or 3.18 over 5 volts, so that's 63%. That's not going to work. So let's go to 16 gauge. Nope. 14 gauge? Almost there. Jeez, 12 gauge? Yes. 12 gauge puts us below 10% drop on our injection wire, which is what we said we would need. Because the problem with 5 volt LEDs is basically, if you compare this with PoE or other standards, those are all devices where you have an input voltage and the output voltage is converted again at the end. So for instance, with PoE, you input 48 volt and at the end 35 volts arrives. That's not a problem with PoE because then the end device converts that 35, 38, 40, 42 volts, whatever is coming in, down to, for instance, 12 volt, which it needs itself, like an IP camera or something like that. So it always down converts. With LEDs, for power injection like this, we have a device that needs 5 volt. So if 3 volt comes in, yeah, that's not going to do much. We need 5 volt. We're not down converting at the end anymore. And that's why we need to size up these cables so much, because we can't really afford much voltage drops. If we input 5 volt, we need 5 volt to arrive at the end. Now, we need to have some margin here. So I have a 10% rule. That means at 5 volt, we can drop 0.5 volt. So 4.5 volt, and we're still okay. That's also within specifications of the LEDs and things like that. Right. So looking at our scene here, we see that we need a 12 gauge cable, which that's already quite a big boy. So that is 12 gauge. Now, the second middle injection is 11 meters away and also 8 amps. So we go back to our scene here and we say 11 and, well, we can now see we're getting 18% drop on that cable. That's too much. So we need to step that down. Let's go for close enough, 11.5%, 0.57 volt drop. Okay, so let's put in that we need 10 gauge for this one. But then it gets worse. Now we need 16 meters and we still need 8 amps. So 16 meters, yeah, that's not good enough. Okay, with 8 gauge, but 8 gauge is huge. But we need 8 gauge cable to basically satisfy the nominal need of our LED strip. That also, wait, one second. Okay, so this is 20 gauge cable. It's relatively thin, but there's still some copper in there. For us European folks, this is 0.5 millimeters square. It's a decent cable, right? And well, this is affordable. It's, you know, it's okay. This is 8 gauge cable. That is a lot thicker. I mean, it's not, well, it's not as thick as my pinky, but it's quite a hefty cable. And let me calculate that for you because I don't know from head. That is 8.3 millimeters square cable. That's huge. And even if that by itself wouldn't be a problem, it's hella expensive. So, and I mean, it's not, you can't screw that into a terminal of any of the Quin LED boards, because it's just an insane diameter cable to get the little voltage drop we need to survive 16 meters for 8 amps that we need to run that LED strip. And this also kind of explains why, if you look around and if people do the actual math, they'll tell you anything beyond 10 meters for 5-volt strip, it's just not feasible, because you run into issues needing cables such as this to even run it nominally. We're not talking 100% here. We're running nominal values here, so single colors and effects. So yeah, there are other methods you can do that. For instance, using buck converters, so you can run 24 volt on the power distribution and then down convert it to 5 volt at the end. But we're not going to talk about that in this video. I do have an article, I'll have that linked in the description, which goes to everything like that. And I might do a dedicated video about that in the future. And well, yeah, I hope that kind of explains why 5-volt LED strips is awesome. It's the cheapest out there. But it's not usable for long length scenarios because, well, you run into these problems. Those are giant cables. But that does conclude this scenario, I think. We know the total amount of power we need, so 140 watts. As I mentioned in the beginning, what kind of power supply do you then need? Well, let's add that. Power supply plus 20%. So that is 140 times 1.2. That is 168 watt. 68 watt. So probably get like a 200 watt power supply. Then you have more than enough margin and you'll always have enough power at hand. Okay. And this also explains fusing. I'm a very big advocate of having fuses in your LED setup. So each injection line should have its own fuse. Why? A 4 amp line that's basically never going to do more than 4 amp, as I showed you in the beginning on my website with my tests, should get a 5 amp fuse. It doesn't matter what wire diameter is behind there. I mean, even if it's this wire, which can easily handle 40 amps, we don't expect more than 4 amps, so we fuse at 4 amps, because if we do draw more, something is wrong. And the same goes for a middle injection. 8 amp should get a 10 amp fuse. Same deal. If we expect 8 amps and it's basically never going to draw more, a 10 amp fuse should do nicely, no matter what cable size is in between there, unless we're talking a really thin cable, because then of course that doesn't apply, because then the cable needs to be able to carry at least 10 amps. But in our cases, all of them can, so that's not a problem. So we know total power, we know total amps, we know the expected power we need for all the injection points, and we calculated all the injection points we need, and we know our fuses that we need. We have the lengths, because those are just the lengths of the LED strip, and then we also know the cable diameters we're going to need to be able to basically provide that LED strip with the current it needs. I hope that makes sense. So let's go to scenario 2. Scenario 2. Scenario 2, we said we're going to use 12-volt LED strip, but in this case we're going to use a special variant. Now, why am I saying a special variant? That's because WS2815 is basically the only single addressable LED 12-volt strip out there. So most strips like WS2811 or SK6812 or WS2814 or etc. are per 3 addressable if they're running in with 12 volt. The reason for that is the LED diodes themselves are basically 3 or 4 or 5 volts basically. So having 5 volt, we can run them at their native voltage. But if we have 12 volt coming in, it can't handle that. So we need to drop down the voltage somehow. Now most strips do this by dividing the power over 3 LEDs. That way you can drop down the voltage in series over those 3 LEDs and you get down to a voltage that the LED can use. The downside, however, is that those 3 LEDs always need to do the exact same thing to always have that voltage drop. If one of them would be doing something else at that moment, well, the voltage drop wouldn't apply and you'd blow up the LED basically. So that's why 12 volt LED strips are generally per 3 LED addressable and 24 volt LED strips are generally per 6 LEDs addressable. Now, as I mentioned, WS2815 is an exception. It is single addressable while being 12 volt. How did they do that, you ask? Well, let's go back to our browser and back to the power sheet, and we're going to back out and we're going to go to the 12 volt sheet. And if we look in here, we have WS2811. That is a version that is, it says it here in the table, per 3 addressable. And we have WS2815, which is single addressable. Both are 300 LEDs, but, well, you can't really see it here. I name this addressable zones. WS2815 has 300 addressable zones because it has 300 individually addressable LEDs, but WS2811 has 100 addressable zones, even though it has 300 LEDs, because they are per 3 addressable. Hope that makes sense. Now, if we look here, we can see something interesting. RGB white 100% uses about 50 watts, 48.6. But 100% red also uses about 50 watt. And 100% green also uses 50 watt, and 100% blue also uses 50 watt. What's going on here? Okay, let's look at that WS2811, which is per 3 addressable. Here we see it only uses 30 watt, 30 watt, 30 watt, while white uses 75 watt. That's the reason, well, that's the difference. By staying single addressable, they had to find a different way of stepping down the voltage from 12 volt to 5 or 3 volt that the LED diode can use. In WS2815, they basically integrated a blind diode, I'll call it. The internal structure is different with a current regulator and things like that. But basically, you should assume that it has 2 blind diodes in there. If you're only using 100% red, the red diode will light up, and 2 blind diodes will light up, and will basically burn the power off that it needs to drop down over 3 LEDs, or over 3 diodes, to make the voltage usable. So if you're using 100% RGB white, well, it'll have 3 visible diodes, red, green, and blue. And if you're using only red, it'll have 1 visible diode and 2 non-visible diodes. Now, this isn't a correctly technical explanation because it works differently in the current chips, but it's a logical explanation I think you can understand. If we then look at WS2811, this one, we see that it works normally like a 5 volt strip would, because dropping the voltage over 3 LEDs is basically 99% efficient versus what WS2815 is doing, which is very inefficient. So, for instance, if you're doing a battery-powered project, I'd much more recommend WS2811 than WS2815, or maybe I'd recommend going with 5 volt, because those are always more efficient. Because WS2815 is going to draw more power. We can even compare that if we say, okay, 100% red uses 51 watts. We then go back and into a 5 volt sheet, and we zoom in here, we see that 100% red uses 25 watts. That means, well, it can mean 2 things. WS2812B is double as efficient, or WS2815 is 50% as efficient. It's basically the last thing, but okay, it doesn't matter. Anyway, it is still a popular variant because most people don't really care, and if you look at effects, it depends on how many LEDs are lit at the same time at which brightness. So here, Police All uses the maximum power, 50 watt. But for instance, orange, 100%, not all LEDs on the strip are lit. And if it's completely not lit, it doesn't use any power except for the standby power. And then we see around 18 watts, or Rainbow 100% uses about 40 watts. But you can go to these sheets yourself and compare what would be best for your project. For instance, WS2811 in this scenario would use about 30 watts, or 25 watts, or 30 watts again. So in some scenarios it uses more, some scenarios it uses less. Yeah. So I hope that makes sense. Anyway, kind of sidetracked here. Scenario 2, we're going to be using 20 meters again. So 5 meters, 16 feet, uses 50 watt. We just looked up in the power sheet. So, that's another reason. I kind of glanced over my conclusion there. This is the reason why we're going to use 100% white power, or red or green or blue, for WS2815, while if we'd be calculating WS2811, we would be able to use the 50% RGB white value. That's the reason, the difference between having it dropped over 3 LEDs, so visually it's less appealing, but it is more power efficient, so you can use the same method as we used for 5 volt LEDs, but for WS2815, we need to use the 100% value. Okay, so 5 meters uses 50 watt. Well, that makes my life easy. That means that 20 meters uses 200 watt. 200 watt divided by 12 volt is 16.66 amps, which is still lower in regards to amps versus the 28 amps we had for our 5 volt strip. So even though it's less efficient, we are using less amps, and since all cables and other things are calculated in amps and not in watts, that will make our life easier. Okay, so let's see the next thing we did. We calculated the injection points. Now we have the same buildup of the strip, because it's again 4 5 meter strips. So let's remove these real quick. We need to inject 16 amps into the strip, or 16.66. Let's say we're wrapping this strip around our room. So we can easily make a front injection. We can easily make an end injection. And, well, we still need more amps, because front is 4, end is 4. So let's inject here in the middle. Right? So we have front is 4 amps, middle is 8 amps, end is 4 amps. Total is, well, I don't need a calculator for that, 16 amps. And we just said we needed 16 amps. Well, that's easy. I'm going to go back up a little bit. Recommended power supply is, let's calculate that real quick. 200 times 1.2. Well, let's say 250 watt plus. Okay. So now we have our front, our middle, and our end, which is already enough. We don't need front, middle, or middle, whatever. We only need 3 injections. And if this is wrapping around our room, our front and our end injection are quite near, so that's easy. Those will both be 1 meter, let's say, and the middle injection, well, that will still be 11 meters because it's past 2 strips. Now it'll depend on the actual layout, etc., but we have strip 1 here, strip 2 here, and again strip 3 here, and strip 4 here. You could say, but hey, you said that we could inject maybe also in this middle. Yes and no. So before I already kind of alluded to this, but if we say a front is injecting 4 amps, but this strip only needs 4 amps, if we then provide front plus middle here, it'll only draw 2 amps from this one and 2 amps from this one. So this middle won't be 8, but 6, and this will be 2. And then we still won't get our total power figure. Another issue that creates, if we inject here and at the end of the strip, the length from over here to the end is pretty long, and voltage drop increases with distance. So if we know the amount of amps we need, it's best to space those out as evenly as possible. And in this case, that's front, end, and middle. You could also do middle and middle. So let's do an alternative option. Let's say front and end and whatever isn't going to work for you for some reason, or you want to run less wires, or you can put your power supply in the middle and your Dig-Quad controller, for instance. Then you can say, okay, I can do middle injection here, and I can do middle injection here. And that would be a valid method of doing it, because we can get 8 amps into this middle. That means 4 amps can go into this strip, and 4 amps can go into this strip. That's fine. Both strips would be satisfied. Then we have a middle here. This strip could then get 4 amps, and this strip could then get 4 amps. And again, we'd be satisfied. Middle 1 is 8 amps. Middle 2 is 8 amps. Let's call this controller in the middle option. Right? One thing to note is that your data connection always has to go on the front. And I'll talk a little bit about another thing we're not going to talk about right now in this video, and that is that at some point you'll have to add a data connection. And actually in these two scenarios you already have to, but I'll get back to that at the end of the video so we can do that quickly. Do I need multiple data connections? So I'll put that there. Now let's calculate both scenarios in regards to cable. So we have a front, middle, end. We said our front was 1 meter away, and we said our end was also 1 meter away, and this was in the middle of 2 strips, so that's 11 meters away. And let's look at the other scenario, which is 2 middles. There, let's say it's 6 meters and 6 meters. Okay, hope that makes sense. Let's copy this again. And now we're going to do voltage drop calculations just like we did before. So we go to our browser, we go to our voltage drop calculator, and well, let's start with 18 gauge. And we only need 1 meter, 12 volt, 4 amps, right? That's our front injection. Well, okay, let's start with 20 gauge. Yeah, well, I don't want to drop below 20 gauge because, as I mentioned before, you do want the cable to be able to handle the amperage more than the fuse you put before it. So let's not drop below 20 gauge is my advice there. So this can be 20 gauge and this can be 20 gauge because we're talking this wraparound room scenario where front and end basically meet near the controller. And well, we have a middle. Let's calculate that. That's going to be 11 meters at 8 amps. Yeah, that's not going to work. 16 gauge? No. 14 gauge. 12 gauge. Well, okay. Let's go with 12. Sure. 12 gauge. So that satisfies our needs. Now, compared with the 5 volt scenario, this is already a whole lot better. Because now we just need 2 20 gauge cables and 1 12 gauge cable. And a Dig-Quad can handle that, or the Dig-Octa system can also easily handle that. I wouldn't advise a Dig-Uno for these 20 meter scenarios because you kind of need some power distribution and fusing and things like that. So, yeah. Now you could say, but well, you changed the scenario, and before the end injection was 16 meters away. Okay, let's take a look at that real quick. If our end would be 16 meters away, we can say, okay, we need 4 and 16 meters. Can we do that with a 14 gauge? Yes. Can we do that with a 16 gauge? No. So 16 meters, 12 volt, 4 amps, because it's an end injection, so an edge injection in that sense. We need 14 gauge. That's still a whole lot better than that insane 8 gauge that we needed for a 5 volt system. Okay, let's take a look at our alternative option where we don't do front, middle, end, but we do first, middle, and third middle, I believe we said. Yeah. So we have strip, first, middle, and then we have second, middle, and then we have third middle. So, well, I still call it middle 1 and middle 2, but, you know, they're spaced out because that's important. Those will both be 6 meters because we'll have our controller here in the middle for whatever reason. It all depends on the layout of what you're building, where would be the best spot for the controller. Of course, you're going to need a data wire that's going from here to there, but with a Dig-Quad or a Dig-Octa system with their built-in level shifters and resistor switchers and things like that, having a 10 or 11 meter data cable generally is no problem. I would advise to run a data cable and a ground cable next to each other, so a 2-wire cable, and then flip that channel to 33R mode. What the hell am I talking about? I'll talk about that a little bit at the end of the videos. Okay, so we need 6 meters of 8 amps times 2, because we're splitting from the middle outward. Okay, so we need 6 meters, 8 amps. Calculate. Oh, can we use 16 gauge? Yes, even better. So now we can say uh, 16 gauge. And, well, again, a Dig-Quad and a special Dig-Octa would be easily able to handle that. Now, as I mentioned, you're going to need extra wire for data to begin 11 meters. Data plus ground. In this scenario, where in the other scenario, our controller is at the front, so you just run the data wire there and you're done. In this alternative option where the controller is in the middle, the data still needs to go to the front. So you need an extra wire for data to front to, you know, bring the data there. And it's actually a little bit more complex than that, but again, we'll look at that after we do our third scenario, because our second scenario, even with an alternative option, is now finished. Here we run front, middle, end. We calculated total wattage or total nominal wattage, but nominal in the case of WS2815 is the 100% value. So we need 16.6 amps. I recommend this kind of power supply. You have a front, middle, and end injection. I didn't talk about fusing, but basically fusing is the same. So I'm just going to copy that. Sure. And in this scenario, we need 3 cables, 2 of 20 gauge and 1 of 12 gauge. If we loop around the room, for instance, so our front and end come back together at the same place. So basically only have to run 1 thicker injection wire. Or alternatively, we can do 2 middle injections and run a data plus ground wire for a data connection to the beginning of the strip. And then we only need 2 16 gauge cables. So even though it's kind of the same scenario, we have single addressable LEDs. The only thing we changed is going to 12 volt. This already makes our life a lot easier. So if you're doing large scale projects or projects in general, I'd say up to 10 meters, 5 volt LED strip, that can work. If you want to do 20 meters, go to buck converters or something like that, or go to a 12 volt strip like WS2815 or WS2811. Its characteristics are slightly different, as I mentioned, with the per 3 addressable, etc. But generally, these calculation values will also work for that strip. But you can now do these calculations yourself using the values from the power sheet. or the real world power sheet. Okay, let's go to scenario 3. And scenario 3, if we look back what that was, scenario 3 is 24 volt, 20 meter, WS2811, 720 LEDs per meter cob LED strip. Now this is very different LED strip. It basically has a built-in diffuser, and it has 36 LEDs per zone. Or rather, it has 12 green, red, and blue LEDs per zone, and then they call it 720 LEDs a meter. If you compare it with the other strips, it kind of comes down to 240 LEDs a meter. Still, let's calculate with that, because that's going to be interesting. 5 meter, 16 feet uses, and well, I don't know from head, so I need to look at my own sheet. And here we have our 24 volt sheet, and the newest addition to that is our addressable neon here, that I call it. And that is WS28, well, it's WS2811. It has 100 addressable zones. So you have a 5 meter strip, and every 50 millimeters or 5 centimeter is an addressable zone that actually has 12 red, 12 green, and 12 blue LED diodes in there, interleaved together. So it makes a really nice diffused effect. Since this is spread over multiple LED higher voltage strip, we can now again use our 50% RGB white value. So that's this one. And looking here, we see it uses, let's say, 60 watts. Okay, 60 watts. So 20 meter or 64 feet uses, well, we're going to calculate almost everything, right? 240 watts. Now you're going to say, wait, that's way more wattage than the other ones. Yes, but I'll also say that this cob LED strip is the most vibrant and I think has the most light output versus all the others. Still, 240 watt divided by 24 volt, well, I really don't need a calculator for that, but that's only 10 amps. So, stepping up the voltage to 24 volt again really lowers our amperage much more again. Now let's quickly say recommended power supply is 300 watt. I could calculate 20%, but yeah, let's say 300 watt. And then we need to do our injections. Now I'm going to copy this one. There. And let's quickly remove this. Because we're kind of in a pickle here. If we want to calculate our injections, we know that a front injection does 4, and an end injection also does 4. But we kind of need 10. Yeah, that sucks. Now let's take a look at the power sheet again if we can get away with it. We calculate with 50% white. But a single color basically uses about 45 watt. So that's already less than 60. Let's keep that in mind. And looking at the effects, none of the effects uses more than the 45 watt of a single color. It's interesting. So let's say we're going to cheat a little bit. And we're not going to be using cheat mode on. We're not going to be using 5 meter uses 60 watt, but we're going to say 45 watt. Now 20 meter uses, I'll calculate, 180 watt. 180 watt divided by 24 volt. 7.5. I'm Dutch. I live in Europe. A comma and then behind it is like, you know, the comma. I don't understand why US people use a dot. It doesn't make sense to me. So we need 7.5 amps for that. 7.5 amps we can do with a front and end injection. So now you have a choice. Are you going to follow the 50% white rule? And this would enable you to do single colors all effects, and even dual colors. And with dual colors, I mean a color that combines, let's say, 100% red and 50% blue to make purple, or 100% red and 100% blue, again, to make another shade of purple. That would use more power. But are we going to do that, or are we just going to run effects? Or maybe we don't care that much if it's full brightness power, or if it then encounters a scenario where it doesn't have enough, we can use the WLED power limiter, set it to 8 amps, and then if one of those scenarios would happen, it'll just lower the brightness slightly. Maybe we're okay with that. Or just, as I said, we're just going to do effects. Because if we use our cheat mode, we could do a front and end injection and leave it at that for 20 meters. That's a whole lot of LED strip for, just a front and end injection. But I actually have 4 of these, and I have tested it, and it works fine unless you ask too much of it. As I said, if you want 100% without any voltage drop of dual colors, you will see some dimming in the middle. Unless you limit WLED to 8 amps, but then the whole strip will be slightly limited so that it's still an even distribution of the brightness. Personally, I feel, depending on what you demand, this could be a viable scenario and would work just fine. But if you're saying, no, I need to be able to run the maximum, well, then you need to do more injections. And for instance, the 240 watt we calculated earlier is already the 50% nominal value. If you say, and this will be the last scenario, scenario 3, ultra mode. Okay, no, wait. Ultra mode. 100% RGB white all the time. Okay, let's go there. Going back to Chrome, and we see here that the maximum the strip uses is 112 watt. Oh, wait, no, yeah, 112 watt. That's quite a lot. Okay, so let's do our calculations for that. 5 meter is 112 watt. 20 meter is 448 watt. Power supply should be 500 watt. You can get one of those nice UHP 500 minus 25s from Meanwell. Excellent passive power supply, can do 500 watt all day long. And very nice. 500 watt divided by 24 volt is... No, wait, 448. 18.66 watts. 18 amps. I'm starting to lose it. Doing too many calculations. Okay. 18.66 amps. Let's go here. And well, we're gonna have to cheat a little bit again because we're just not getting there. Because if we do front, well, I can just copy this from here. Because it's basically the same scenario as that. Total is 16 amps. Now, I'm thinking this will be close enough because we're in these calculations we're saying that basically the strip is not transporting any power at all, and all the power has to come through the power injections and yada yada yada. That's not fully true. I'd say this is close enough, right? There's always a little bit of margin there. But that also means we already know what kind of cables we need for that, because, well, this scenario basically just applies. It's the same scenario. It's the same calculations. It doesn't matter if it's 5 volt, 12 volt, or 24 volt. Calculating amps is amps. And that cable can carry that much amps with so much voltage drop. Now, that's not completely true. So, if we take a look at our middle injection here, we needed 11 meters with 8 amps. But that was our 12 volt calculation. Let's go to our voltage drop calculator real quick. And we're saying we need 24 volts, or yeah, for 11 meters and 8 amps. Hey, now we can use 16 gauge. But before, we said we needed 12 gauge. Why is that? I explained this before. The 10% rule scales with voltage. So at 5 volt, we can drop 0.5 volt. At 12 volt, we can drop 1.2 volts. And at 24 volt, we can drop 2.4 volts. And in this case, it means that we end up below the 10% drop figure, where if this was 12 volt, we wouldn't. Right? Because now we're dropping 2.3 volt, which indeed makes sense, which is below the 2.4 for 24 volt, but not below 1.2. So we can copy some of it, but we still have to do the calculations. So we can use thinner cable here for a middle injection. And again, a Dig-Quad or a Dig-Octa would be a perfect fit. So, well, we already kind of started bodging the last scenario into multiple versions and Uber modes and things like that. I'm hoping this makes it clear how to calculate your own LED setup that you want to build. Figure out the total wattage, figure out the amp that is at the voltage you're going to be using for the LED chip you're using. With that, you can figure out how many injection points you need. Front will do 4, middle will do 8. You need, I don't know, 20 divided over the points you have, evenly spaced out as much as possible. Then you know your injection points. Then you also know the distance to those injection points. Calculate with distance and amps using the voltage drop calculator. And now you know everything you need. Wire diameter, power supply, fusing, injection points, everything to run a nominally correct and well-functioning LED setup. Right? I'm probably going to repeat that one more time. But so there's 2 more topics to discuss. Do I need multiple data connections? And 33R resistor mode. Now, for do I need multiple data connections, I'm again going to refer to an article on my website. We go to digitally adjustable LEDs, and then we go to what is the maximum amount of addressable LEDs per controller. Is this at 100%? No. So here, and I'm going to scroll down a little bit. Basically, in short, the technical part of it is the WS28, 11, 12, whatever protocol is a fixed rate protocol. So that protocol always runs at 800 kilohertz. If you have 100 LEDs, that means each of those LEDs can get 333 updates a second. Now that's well above human visibility, right? But if we now have 500 LEDs, you're now at 66 updates per second per LED. And we generally want to be around 60 frames per second to have fluid motion. Now, WLED by default, you can now set it in the newest versions, runs at 42 frames per second. How many LEDs can we then run with our fixed rate protocol? 793.6. I already did the calculations for you. That is, however, without any overhead and any hiccups or things like that, or the processor on the ESP32 taking just a little bit longer. So I generally say for a single data output, you don't want to connect more than 600 LEDs. That keeps you nicely above the 42 frames per second at 55 frames per second. And, well, that works very nicely for, the data outputs. But then in our scenarios, we're connecting 5 meters with 300 LEDs times 4. So that's 1200 LEDs in scenario 1 and in scenario 2. Scenario 3 is different. So let's take a quick look at that. Do I need multiple data connections? Scenario 1, yes. We need 2 times 600 LEDs. Well, here's a copy, yes. And again, same thing, we need 2 times 600 LEDs. Scenario 3, however, no. 1 times 5 meter is 100 addressable zones. Times 4 is 400 zones. So since it's not per single LED addressable, the amount of addressable LEDs goes down. That goes out of a single data port. And now we only need one single data channel. So even for scenario 2, if instead of with WS2815 you'd gone for WS2811 with per 3 addressable, that means we don't have 1200 LEDs in total, 2 times 600. We have 1/3 of that. So, math. That is again 400 zones. Okay, so with WS2815, you need 2 data channels and you need to wire that up. So you need to have 2 strips together of 600 and you need to cut the data connection. And then you have another section of 2 strips of 300, so 600. So you'll have to have 2 data wires coming from your controller, one to the front of the strip, then you have strip 1, strip 2, cut data connection, and then run another data wire from your controller. And if this is a long length, I recommend running 2-wire cable, so with the data signal and ground together in that cable to the third LED, the front of the third LED strip, have the data cut there, and basically inject data there from the second LED channel to keep those 1200 LEDs in total running at a nice and good frame rate. Hope that makes sense. And well, depending on the type of LED, you got like, a 12 volt, 24 volt WS28, well, that's a good one, 2814 or SK6812. There's a slightly different thing there. RGB versus RGBW. The above values are calculated with having 3 diodes per LED chip. But if you now have 4, that's going to eat up basically some time of our fixed rate protocol. So now to keep 60 frames per second, we can only do 416 LEDs, or to keep 42, which is the default, we can have 595.2. So for RGBWs, I try to keep within 500, but if you really can't, because the strips are 5 meters with 300 LEDs, you can do 600, but your frame rate will drop a little bit. It's not that like it's not going to work, but the animations will just have less points to go to basically, so it'll be a little bit choppier. But then again, if you move to 12 volt WS2814, TM1814 or SK6812 or 24 volt variants of those, while the amount of addressable zones drops quickly with the per 3 and per 6, and then it's again much less of a problem. Okay, I think we've said enough about that subject. The last thing on our list is 33R resistor mode. What the hell is that? Well, we go back to our website, we go to addressable LEDs, and there's an article and a video there called The Myth of the LED Data Resistor or Data Signal Cable Conditioning. And basically, all of the dig boards, so the Dig-Uno, the Dig-Quad, and the Dig-Octa nowadays have a resistor switcher on board. And it depends on what type of cable you're running. Either you're running a data wire or you're running a data wire with ground close to it, if you need to be in 249R mode or in 33R mode. The default mode is 249R because that works for short distances for any setup, and it basically delivers a cleaner data signal. But if you have a long data wire, run ground next to that data wire, so have a 2-wire cable that's basically attached to each other. Cable like this, normal cable, or I'll show you this variant, I guess, and then flip that channel with the dip switch on the dig board to 33R mode, which is optimized for having ground next to your data wire. That will work a whole lot better. Okay, I think that does it. As I mentioned, I'm going to mention it once more. We now know how to calculate total power usage, so we can figure out what power supply we need. We know how to convert that to amps. Because we know the amps, and we know a single edge injection will do 4 amps, and a middle injection will do 8 amps, we know now how to divide our total amps that we need over the injection points, and generally inject in between or at the front or end of a strip. Just to make it easier, you can inject at any point, but then you have to solder. And generally these strips come with those little two pigtail wires attached. If we, at the front of this video, we already tested that, and we can use those. We don't need to change those for thicker cables, and we can inject power there. That's a good point. If you need to run a thick 12 gauge injection cable, you need that cable for the distance, not for the amount of amps we're going to push over it. So having a small pigtail come from the controller, then the thick cable for the long distance, and then again a small or thinner diameter wire for injecting onto the strip, because you can't solder a 12 gauge to a strip, that's fine. We need it for the distance, not the amount of amps. A good tip to remember. Anyway, we now know how to calculate what wire diameter we need for each of those injection points. And, well, I think that's everything you need to know. Now you can calculate your own scenarios. And I always tell people, come to the Discord and we'll help you out. But if you've already done a schematic drawing, even if it's in paint or on paper or whatever, and watched this video and did these calculations, we much rather verify your setup than have to think how to design your setup for you. And we'll give tips like, hey, you could move your controller here. That means these power wires that carry 8 amps can be shorter and thus thinner and cheaper, and things like that. We'll help you with that. But try and do your initial design yourself. And if you then want us to verify it, or hey, like, should I use a Dig-Quad or should I use a Dig-Octa? Can I run this on a Dig-to-go? Come to the Discord server and we'll happily help you out with those things. You can also comment on this video and I'll try and help people there. But it's hard to do that in YouTube comments, and I'd really rather you come to the Discord server where we can just chat and share images and things like that. Well, this was an hour-long video, which I wanted to be really short. So I did a great job at that. But I hope my explanations were better and you now actually understand what's going on, why we need to do this, and how to solve the problem. Okay, catch you in the next video, guys. Bye-bye.